right, hey folks, we're back. I'm joined by Anthony Shaw.
Hey,
𝗏𝗏𝗀𝗀𝗏𝗏𝗏.
Tony Baloney's on the stage. Hey, Burke, how's it going?
Yes, good, I'm doing well. You are a technical advisor.
I am, yeah.
Yes, and previously Python advocate at Microsoft.
I've been working on Python for 5 years at Microsoft, yeah.
There's like, am I supposed to read this entire bio? There's like
No, it's fine, don't worry.
things. You won a Nobel Peace Prize?
Only a couple of them, yeah.
Amazing, unbelievable. All right, now, literally the title of this session is, the next 16 minutes is, this sentence makes no sense. Is Doom a tensor? Yes, and why? Yes, here, and yes, and here's why. What does this even mean?
Okay, we're going to do
and by the way, this is not what we agreed to talk about.
What did I agree to talk about?
No, you sent me a message. You were
like,
IQs. I'm so sorry, you're going to hate me, but we're doing this instead.
Yeah, I thought we'd just go on a bit of an adventure in this session over the next 20 minutes. And we're going to talk about tensors. I'm going to explain how CPUs work, machine learning models, inference. We're just going to go fast and go quick.
In 15 minutes.
In 15 minutes.
Best of luck.
OK, so is Doom a tensor? First of all, what is a tensor? So if you look at something like an Onyx model, a tensor is some data which has a size and a shape. So normally we represent these as like a matrix. So for example, if it was an array that is one dimension and it has 4 items, and then we had a model that outputs 1, then it could be the numbers 1, 2, 3, 4, and you could run the operation sum, and it would give you back one number, which would be the number 10. That is the simplest machine learning model I could come up with. All it does is add the numbers together. It takes a sequence of numbers and returns you back the total. So we're gonna go deeper and deeper and deeper until I make Burke cry, okay?
I'm already there. It only took one slide.
Okay, so that is the simplest one I could think of. Here is a tool that I love to play with called Nectron. Nectron allows you to actually inspect AI models and explore what's inside them. So yesterday we announced a whole bunch of new MII models, image models, there's reasoning models, there's all sorts of stuff. I love to actually just explore what's inside them, how do they work. And the way that we can do that is in Nectron, we can actually open up one of those models. The model that I've got on screen is a text embedding model called Harrier. And inside there, you can see this is basically the graph that explains how to actually execute this model. So the input to the model is your tokens, so like the text, and then also something called the attention mask, which we definitely don't have time to explain. So
I do know a thing about attention. We should have a whole session on attention because that's the most interesting part.
Okay.
Sorry, go ahead.
So you might think that a model is basically just some weights. That's not entirely true. It actually has instructions to explain how you take the weights, the user input, and you process that through the different layers to get the output tokens. So that's what it kind of looks like inside. I was looking around at this, and I've been focused on thinking about how some of these nodes can be optimized for some new hardware that we've got coming out. I don't know if you heard that announcement.
I did. I was coveting it, but I don't think they're going to give it to me.
Okay, yeah, we have, so we're working on a project with NVIDIA. We've got this new Windows Surface device, the Surface Ultra.
I believe so.
The Ultra.
With what, 128?
Up to 128 gig of RAM.
Of unified RAM?
It also has on the SoC, it has a GPU. So I'm really excited about how we can make that work.
Yeah.
But I noticed that Onyx itself is Turing complete. Some of those instructions include ands, ifs, loops, stuff like that. So I thought, if an Onyx model is Turing complete, can it run Doom? Okay, can you see where this is going? No, you're still getting there. Okay.
I'm 50% with you.
Okay, so to answer the original question, is Doom a tensor? We're going to get there. And we got 12 minutes. Okay. Now, hopefully you're familiar, but we announced this a few builds ago. This was in 1995.
Jeez, Bill Gates looks younger than I am right now.
Doom runs on Windows. So we've got that one nailed. There's absolutely no reason to run it in a tensor, but it's fun because we get to explore how they work and how Onyx models are put together. So
Onyx is the model, right?
Onyx is the model, and it includes instructions to how to take the user input, the tokens, process it with the weights, and compute the output.
So would it be accurate to say the question is, can an LLM run Doom?
Yes.
Okay. That's a bizarre. I don't believe you. I know. That doesn't even make sense. They can't spell strawberry.
So I thought, what is the lowest level of compute that somebody has run Doom on? And is this project called Potato Doom?
No.
Potato Doom, essentially they created a string of potatoes and used that string to power a small device which ran Doom.
Okay, so the potatoes aren't running Doom. They're just powering the device that's running Doom. That's a little bit of misinformation. Fake news.
Okay.
Fake news.
So I thought, if we're going to figure out in our Hobbit land, how are we going to get this running in a model? I think we have 3 options.
Is this an AI image?
Maybe.
Okay.
Option 1 is write a C compiler, so we compile Doom from source into Onyx. That's option 1.
Okay.
Option 2 is create a CPU emulator. And option 3 is go for a war. Who's in favor of option 1 in the audience? Nobody. And option 2. Yeah, that's good. Okay, option 3. Okay, a few of you. Okay, option 2 is the correct choice. If this was an adventure game from the 90s and you pick option 1, option 3, you've lost the game. It's game over, I'm afraid. So I thought, okay, what would be a simple CPU that we could emulate purely in Onyx nodes? And the answer would be the RISC-V architecture, because it's fairly straightforward. We can actually, it doesn't have that many types of instructions. I can compile Doom from source into machine code, and then I can interpret that machine code purely in Onyx. Do you believe me, Burke?
I mean,
or am I losing you?
I'm just a JavaScript developer.
Okay. So with this, I had a little bit of a trick up my sleeve, which was that I described this problem to Copilot and said, Copilot, this is my idea. I need to get this working for tomorrow. Are you on board?
Oh, you did it yesterday?
No. This was a week ago. Okay. And I started off with Opus 4.7, and it wasn't convinced. It said this would take several weeks. And I rolled back to my old friend, Opus 4.6, because it is a bit more gung-ho.
Yeah, it is getting a little bit more like, nah, I'm not doing that.
It tries to talk you out of things, I found, with some of the newer versions. And I'm like, I need you on board for this project, because we need to make this work. So I didn't have a disassembler to hand. So I actually compiled Doom into machine code, and I wanted to show you what that would look like. So I've put together a disassembler in a different tool that we can use, which is, are you familiar with this one?
Excel?
Okay, yeah, that's it. This is Excel. We can actually just read Doom in Excel, and we can disassemble it in Excel. Because there are not many instructions in the RISC-V instruction set, we can just do this entirely in Excel formulas.
This is so cursed. Everything about this is cursed. It just gets worse.
Okay, we're nearly there. So if we can understand and read, just using Excel formulas, machine code, I had a question. This is going to get worse, Burke.
Okay, please.
If Excel can read the machine code, can it just interpret the machine code for me?
And you're going to run Doom in Excel.
Yeah, so I thought I added another spreadsheet.
Wait, is Excel Turing complete?
It turns out yes is the answer.
No way.
So I added a sheet which is the program, and then I added a sheet which is the memory or the RAM. So the RAM would get stored there. And then I basically just added the registers as columns in the spreadsheet. And you can just do flash fill in Excel. The problem with this implementation is that you have to keep dragging down, otherwise you run out of instructions. And Excel, unfortunately, only has up to about 1 million rows. So
oh, really? There's an upper limit?
There is an upper limit. And you discover that by doing experiments like this.
You found it?
We found the upper limit.
At which point what happens? Like the whole thing just freezes?
I think it just runs out of letters on the left-hand side.
Like literally there's just no more rows? Oh, no.
So there's nowhere for it to go.
This is like going to the end of the internet. Like, have you seen, you remember that commercial where it's like you have reached the end of the internet and the guy's like, there's nothing else to do? You reached the end of the internet.
We've reached the end of Excel. Okay, so That's point 2. Doom runs on Excel. I think we've ticked that box.
Did we already know this?
No. This is new. This is live and announced at Build 2026. I've created the promotion.
Yeah, here it is.
We've added this promotion to our Build announcements. It should be in the...
Why is it all from 1985?
This is AI. This is AI generated.
Oh, okay.
Yeah, I asked AI to make me a 90s-looking advert showing how Doom runs in Excel. Okay, so can we run Doom in an Onyx graph? So that's my next demo. So I'm going to show you Nectron. And what I did with Nectron is I basically built a graph that represents a CPU. And the inputs to our model are the game, which is 8 megabytes of RAM, and also the compiled game, and the CPU itself. So I have to zoom out because it's a bit big. So this basically represents a RISC CPU, and it's got all the instructions in the RISC CPU, and it can process those nodes, calculate it, and basically treat the RAM as a tensor.
Okay.
Okay. Now, would you like to know how fast this is? How long do you think it took for it to output this frame?
One single frame.
Yeah.
Yeah, how long did it? It's got to be something like 30 minutes.
So I set this running, and I was going to one of my kids' soccer games. It was a long drive to get there, and I said to Copilot, when you get the first frame that is not just black, I want you to go and drop it in my OneDrive, and then send me a ping on Teams, so that I can just have a look at it and see what it did. And I'm jumping around like a silly person on the soccer pitch because I saw this flash up, and I'm like, I can't believe it worked. But it was 6 hours.
What is the frame rate on that?
So I don't know how many decimal places it was, but I worked out if this was a CPU, it would be 2,000 hertz, or 2 kilohertz. It would be a 2 kilohertz CPU. So I had a bit of a conversation with Copilot. I was like, your graph implementation of this Onyx model, this is not performing. Like, what can we do about this?
Very well. There's room for improvements.
So that's where I want to kind of change the tangent of this talk from something entirely pointless and exploratory into actually what can we do in scenario areas like this where Copilot or something like it has put together something and you're not happy with the performance. Now, my tips with performance generally are like work with the cheapest and easiest thing first, which is caching. It's always caching. You just cache the output. I think like computer systems these days are just caches and caches and caches. So for Copilot, I'm like, okay, how can we cache the output?
Okay.
It couldn't do that.
It couldn't cache the output?
No.
Okay.
The other option is you reduce work, so you just reduce the amount of compute that you have to do. So after a couple of iterations, it compacted that graph and actually thought about it and tried to reduce the number of nodes. And the next option is...
How much did you get out of that, number 2?
I got to about 4 kilohertz.
Okay. Just one image every 5 hours?
Yeah, I think it's three frames, 1 frame per 3 hours.
Okay,
yeah.
there we go.
So not quite playable. And then the other option is scale up, where you just make the computer bigger. This is currently the biggest computer we sell. It has a ridiculous amount of processing power.
Is this the Ultra?
It is not, no.
It looks like it.
I would be in trouble for bringing that on stage.
Oh, okay.
Yep. And the other option is scale out, but unfortunately, Doom is single-threaded. So my tips for coaching AI agents on speed is that when you start them off, you need to give them a benchmark at the beginning, because otherwise they're going to make a bunch of assumptions about how to make things faster, and they're not going to base that on facts. They're not going to base that on reality. They're just going to jump in and be like, oh, we could just parallelize things, or we can introduce threads, or they're going to try all these new approaches. But if you don't start with a benchmark, it's kind of guessing whether or not it's going to be faster or slower.
Okay.
The other thing you can do is you can use the contrasting hypothesis or the rubber duck. Have you used the rubber duck feature?
Yeah.
Okay. You can use the rubber duck, which is a really cool feature in Copilot CLI, where it can kind of review things for you and challenge it. And then you as a human are the kind of one who actually has to look and see, like, did the thing that it do to optimize that make it faster?
Yeah.
So here is the working demo of the final result. I've sped it up by about 1 million times. Otherwise, we would use up the remaining 2 minutes. This is the Onyx model. Unfortunately, Onyx...
How are you clicking? How are you...
Onyx doesn't have a screen. It just outputs numbers, so you have to take the frame buffer and then convert it to a GIF. But yeah, that's the only downside with that implementation. There's no keyboard controls, there's no sound.
Well, who's firing the gun?
It's the demo reel for Doom, yeah.
Oh,
so it's running the demo program.
It's just running the demo program. Wow. How many tokens were burned on this?
I think it's best I don't answer that question with Martin within earshot of me. Hey, Martin.
Is Anthony above me on the leaderboard? Aha! I'll take that.
Oh, there is no such board.
There is. Oh,
so, to bring this back to something concrete, yes, Doom is a tensor. That's brilliant. This is not efficient. It's not a good idea. I don't recommend doing this. The thing I do want to talk about, though, is that these nodes in your model, they are specific to the computer that you're running on. So like some of these, for example, in the Harrier model, matrix multiplication is specific, like the implementation is specific to the CPU, GPU hardware that you run on. So I think what's really important is that if you download a model from Hugging Face or something like that, you need to understand, is it actually optimized for the hardware that you're running on? Just because you've just bought a new GPU or you've just plugged in something that has a Tensor core or an NPU doesn't mean it's necessarily going to be faster. In most cases, it doesn't actually know how to use it. So you definitely all need to learn a bit more about these models. That's my summary. Thank you for coming to my TED Talk.
That was amazing, man. That was amazing. I love that. I'm going to be honest, I think I've learned more in the last 15 minutes than in the previous 6 months. So I appreciate that. And most importantly, we learned what we already knew, which is that you are a million times smarter than I am. All right, get out of here.
Copilot.
All right, we'll be right
much.
back. Thank you.
All right.